differentiability, and this is what I'm recording. For differentiability, again, all that is a fancy word for is saying, can we take the derivative? Now, the first thing that we need to be able to take the derivative is we need for that function to be continuous. If the function is not continuous, then it will not be differentiable. That's the first thing we look for. So like 1 over x. F of x equals 1 over x. Where's this function? Oh, let's do 1 over x plus 1. Where is that function not continuous? -1. At x equals -1. Yes. If you cannot. You're good. You're good. That was messy. Okay. All right. Now, the next thing that we need in order to take the derivative is we need for us to not have a corner or a cusp. Yeah. A good example of a corner is f of x equals to the absolute value of x, right?
Right.
Boom.
Yeah. So if you think about it, you look at the graph here, it's like, all right, well, my slope over here is always -1, right? My slope over here is always +1. What is it right there?
0.
It's undefined.
Okay. Wait, that's not moving.
Do you approach it from one side?
It doesn't matter if it's moving or not. It's just, you've got a corner here. For a derivative to exist, the limit of the derivatives have to be approaching the same thing from the left and the right. I don't usually go over that, but that is true. Huh?
So there's technically a hole at 0?
No, there's not a hole. It is continuous, but it's just not differentiable. Now, this is important. If a function is differentiable, it is automatically continuous. But if a function is continuous, it is not automatically differentiable. The two usually do go hand in hand, but they don't always. The cusp looks like, okay, let's say we have y equals the absolute value of the cube root of x. Absolute value of the cube root of x. That would look like, all right, the cube root of x looks like this. Okay? Now, the absolute value of the cube root of x looks like this. In other words, these turn positive. So at that point right there, the limit as the limit of the derivative going in this direction is -infinity. The limit of the derivative going in this direction is +infinity. So you basically, you don't have two hard numbers like this. You're on the absolute value, you were -1 and +1.
So your 0 is still undefined, or 0 is defined?
Yeah, the cube root of 0 is 0.
Yeah.
So it is defined, so the function is continuous there,
Okay.
but it's just not differentiable there. Yes?
What's that third rule?
No cusp.
Cusp.
No cusp. Yeah, CUSP. All right.
What is that mean? Is like when it hits 0 and there's not really anywhere like to go to?
Kind of branches off opposite.
All right. When what hits 0?
The cusp mean when there's like a sudden change in direction of the line?
Well, I mean, you kind of got a sudden change of direction here too. But yeah, that is happening there. But a corner is you've got like a solid derivative of -1 here, a solid derivative of +1 here. But a cusp, the derivatives are constantly changing. They're just growing towards -infinity, +infinity. Yes.
I think that was going to be my question. So a cusp is like, well, if the limit's -infinity and +infinity, then it doesn't exist, right?
Yes. The derivatives don't exist
So
there.
the
Yes.
derivative doesn't exist from each.
Yes.
But it's still continuous. And at the corner, the derivatives do exist from each direction, but they're different.
Yes.
Okay.
Yes. And that can also happen in a piecewise. It doesn't. A corner doesn't have to happen in a. What am I looking for? An absolute value. You can have a corner occur in a piecewise function. You could have a piecewise function that does this right here. You got a corner there. So it doesn't have to be necessarily an absolute value. And then finally, I'd almost forgotten to include this one, a vertical tangent line. A vertical tangent line. And a vertical tangent line comes from the cube root of x. Let's take the derivative of cube root of
There
x.
is or isn't a vertical tangent?
There is a vertical tangent line on the cube root of x at 0.
No, like, the derivative should or should not have a vertical tangent.
Should not.
Oh, okay, I was
Okay,
confused,
so
'cause
no
it said,
vertical tangent.
all the other ones said no in that.
It's going to make sense in just a second.
Okay.
So, all right, if f of x equals to the cube root of x, that means that f of x is equal to x to the 1/3, right? Okay. Now, what is f prime of x? 1/3 to the -2/3, right? Which would mean f prime of x equals 1/3 x to the 2/3. All right, now, what is f of 0?
F of 0, that undefined.
No, f of 0. What is f of 0?
Oh, f of 0, 0.
F of 0 is the cube root of 0, which is 0. But what is f prime of 0? You get 1/0, right? So it's undefined. So if the derivative is undefined, then it wouldn't be differentiable there. But graphically what's happening is you have a vertical tangent line there. So
That makes sense.
So there should not be a vertical tangent.
there should not be a vertical tangent line. Function has to be continuous. You can have no corner, no cusp, or no vertical tangent line.
Okay, that's why I was confused, just because it
Wait,
said
so-
no.
That's like,
Go ahead, William.
wouldn't it not be continuous either if there was a vertical line?
Yeah, it's continuous because you've got, what is f of 0? 0, right? What is the limit as x approaches 0?
Got it. Okay,
Still
that makes
0.
sense.
So y'all are asking great questions because you're thinking. Yes.
So it's like an asymptote, but for the tangent line, because it's the derivative.
Yeah, if I graph the tangent of this, oh gosh. If I graph the derivative of this, it's increasing to the left of the y-axis, right? And we are we're still increasing, right? We're still increasing here, but here it's steep and then it gets closer to 0. So the graph of the tangent line of the cube root of x looks something like that.
So, okay.
So the derivative would have a vertical tangent.
So-
I mean a horizontal, vertical asymptote there.
This is what we were talking about earlier, where if the derivative of it is discontinuous at a point, then it's not differentiable at that
Yes.
point.
Did y'all catch what he said there? If the derivative is discontinuous at a point, then the derivative is not differentiable there. And that's what's happening in these three cases.
Wait.
The function is continuous there, but the derivative is not continuous. Yes,
So for
differentiable.
to be differentiable, can it be differentiable at a point, and can it also not be differentiable as a whole?
Like the same way that continuity, something can be continuous from like on the interval like 1 to 3, can something be differentiable on one interval and not differentiable as a whole?
We're differentiable on open intervals. We're not differentiable on closed intervals. At a point, if you only have a point plotted up there, that would not be differentiable.
But if the point is on a line?
If the point is on a line, then the function would be differentiable at that point, but that point is part of an open interval. And that gets confusing.
What's the definition of
Open interval,
That's the first
an open interval is an interval of A to B where A and B, A is less than B, and A does not equal to B. Well, if A is less than B, then A couldn't equal to it. So, in other words, an interval covers a range of numbers, and that range is infinite.
That makes, so it can be on an interval, it just has to be open.
We are differentiable on an open interval, yes.
So like, could we take, for instance?
Wait, let me finish answering her question real quick.
Okay.
All right. So when you're talking about this at a point, like let's just say that this is the point 1, 1. It is differentiable at that point 1, 1. It's continuous at that point 1, 1. I can plug 1, 1 into the derivative and get an answer. So it is there is a derivative at that point, but when we're talking about differentiability, we mainly are talking about over intervals. All right. Go ahead, Annabelle.
So, could we, for instance, take left, like in the equation, the absolute value of the cube root of 3, or the cube root of x. Could we take like
The absolute value?
Yeah.
Okay, this one right here.
Yeah. So could we take, for instance, like I don't know, x is the interval between where x is 3 and where x is 15. Would that be? We can say that interval is differentiable.
Yeah, from 3 to 15, it's differentiable. This is differentiable from negative infinity to 0, and then 0 to infinity.
Okay.
That's where this is differentiable. Did that help? So anything that's like any set. This is neat. This is a neat question. Any set inside of this open interval is so. 3 to 15 is in that interval, right?
Yeah.
So if it's continuous for this interval, then it would be continuous. It would equally be continuous in the interval that is a subset of that interval.
Okay. All right. I think I understand.
Any other questions?
Quit teaching.
The bell ain't rung yet. 'Cause I still teach 3 minutes after the bell rings. I know. You can have the rest of it. All right. Okay, so that's a good one to end on here.